Hello, class. So on this video, we'll continue on section 3.2/4.1. In the previous videos, we've been talking about a couple of new things. We introduced the concepts of linear independence and linear dependence. And we also introduced the concept of, or not the concept of, but a method to determine whether a set of functions are linearly independent on a given interval, right? That was the method using the Wronskian, which you saw was a little bit better, at least in terms of the work, than actually using the definition of linear independence, right? We did a couple of examples just using the definition, and it was a little bit more theoretical, like a little bit more theoretical arguments for that. But the Wronskian gives us a way of finding whether a set of functions are linearly independent on some interval, and doing it in a way that's basically just computational. The only thing is that, of course, it's not the definition, so it's a little bit less powerful, meaning that sometimes our interval won't be as large as it can be. Right? We saw that in one of the examples. But like I said, most of the times, the intervals that we get are big enough, or they match the intervals that we're interested in. Now, why are we going through all of this? Why are we defining all of these concepts that only work for linear, specifically homogeneous differential equations? So why define linear independence? What's the point of this? Well, the point is that we want to find a way to find the general solution of a differential equation that is not separable, that is not exact, right? And then what else do we do? Or that is not first order, right? So how do we deal with linear second order or third order or fourth order differential equations, right? How do we find the general solution? Well, the way we find it is going to rely a lot on what we're going to talk about now. And it's based on linear independence. Okay? So definition 5. Any set of y1, y2, yn, so we have n solutions. Okay, so any set of n solutions that are linearly independent and that are solutions to an nth order homogeneous, and remember when I say homogeneous, that implies linear, ODE on some interval I is called a fundamental set of solutions on that interval. Right? This is going to be important. So if you have an nth order homogeneous ODE, doesn't matter the order. Let's say it's a fifth order homogeneous ODE. If you have 5 linearly independent solutions, so as many solutions as the order of a differential equation that are linearly independent on some interval, we call that set of solutions a fundamental set of solutions. Okay. Now that we have this, we can go to basically the main theorem. Why this theorem that we're going to see now is the reason why we talked about linear independence in the first place. So let y1, y2, up to yn be a fundamental set of solutions to an nth order homogeneous ODE on some interval I. And this is the great part. Then the general solution for the ODE is given by, well, any linear combination of these solutions. Right? So y equals c1 y1 plus c2 y2 plus cn yn. There should be a plus there. Where the c sub i's we know are arbitrary, right? By definition of what a linear combination is, right? We usually take them arbitrary. We can take them to be specific, but in this case, they can be arbitrary. And of course, this is on I, on whatever interval that the functions are linearly independent for to begin with. What this means is, if I gave you a homogeneous, and we'll see this in an example, in the next example, but if I gave you a homogeneous fifth order differential equation, and I gave you a fundamental set of solutions, right, that is 5 linearly independent solutions on some interval, then the general solution is just this, all possible linear combinations of those linearly independent solutions. Now, why is this great? This means that if we want to find a method to finding the general solution for higher order homogeneous ODEs, right? So we know how to do it for linear ones. I use integrating factor. But what if we had homogeneous second order and higher ODEs? Well, what this theorem is telling us is what we have to do is find linearly independent solutions on some interval. Once we find enough linearly independent solutions, right, namely as many linearly independent solutions as the order of the homogeneous ODE, then we're done. We know what the general solution is because it's going to look like that, what's underlined in red on the interval I. Now, if you have taken linear algebra, what's happening here is that what's happening is that the set of solutions actually forms a vector space. So the set of solutions for an nth order homogeneous ODE on some interval is an nth dimensional vector space. So what we're saying here is that the y sub i's, right, or the y1, y2 up to yn, linearly independent solutions form a basis for that vector space. So that's the linear algebra behind it. If you haven't taken linear algebra, don't worry about anything of what I said now. Right? Just worry about what I've been saying, what I've said before that. Right? What this is telling us is if you want to find the general solution for a homogeneous nth order ODE, what you have to do on some interval, what you have to do is find a fundamental set of solutions on that interval. So again, powerful because this is telling us, or giving us an approach of how to find general solutions for higher order ODEs. Okay. Now let's see an example. So let y1 be e to the 3x and y2 be e to the negative 3. Now, these form a fundamental set of solutions for this differential equation, y double prime minus 9y equals 0 for all real numbers. How do we know this? Well, you can verify, right? You can plug them in and verify that these are solutions. And in the previous video, in example 8, we verified that they're linearly independent for all real numbers, right? So negative infinity to infinity. So we have a second order ODE. We have two linearly independent solutions on I. So by definition, they form a fundamental set of solutions on I for this differential equation. What does this tell us? Well, the general solution for this ODE is any function that looks like this. An arbitrary constant times y1 plus an arbitrary constant times y2, which in our case is c1 e to the 3x plus c2 e to the negative 3x. And this is the general solution for all real numbers on I equals negative infinity to infinity for this differential equation. Again, notice that it's second order homogeneous, so this is by definition what we're looking for. So what we're gonna do in the next chapter, or not the next chapter, because it's still gonna be chapter 3, but in the next videos is find or define a method to how to find these linearly independent solutions. Because again, once we have them, we have the general solution on whatever interval they're linearly independent. Okay. Now, the last theorem. Given an nth order homogeneous differential equation, is there even a fundamental set of solutions on some interval, right? So does it even matter, or is it even worth for us to try to find a fundamental set of solutions? And this goes back to what we talked about in Euler's method, what we talked about in the existence and uniqueness theorems, that if we know that no solutions exist, there is no point in looking for them. But this theorem answers the questions for us. This theorem is saying that there always exists a fundamental set of solutions for any homogeneous nth order ODE on some interval I, right? So we don't know what that interval I is, but we know it exists, and we know that on that interval, a fundamental set of solutions exists. Right? So what is this telling us? That it is reasonable for us to actually try to find the fundamental set of solutions because we know it exists. Now, I'm not proving this, but if you take in linear algebra, the reason why this is true is because every finite dimension or any vector space, whether it's finite dimensional or infinite dimensional, has a basis. And that's the idea. Right? That's where this comes from. Again, if you haven't taken linear algebra, don't worry about that, and don't worry about the proof. I don't even think that they prove it in the book. So don't worry about it. What matters to us here is that we know a fundamental set of solutions exists for any, doesn't matter what it is, for any homogeneous nth order ODE. So it's reasonable for us to try to find that fundamental set of solutions. And as we saw, if we can find the fundamental set of solutions on this interval, we can find the general solution on this interval. Okay. So this is the conclusion of this two sections, 3.2 and 4.1. And this is the reason why we introduced all this terminology about linear independence, because it's actually the way we're gonna find the general solution to higher order ODEs.